Okay, so the midline is halfway between the max and the min. In this case, it's 2. And the amplitude is, the amplitude is the distance from the midline up to the max. It's also, that's also will be the same distance from the midline down to the min. And we call it capital A. The amplitude. So if this were circular motion, relative to the circle, what would that value of A represent? What would that value of A represent in circular motion? This is circular motion. So the midline, if we're talking about cosine, the midline means neither to the right nor to the left of the vertical diameter. So when we go from that midline out to the max, how far? That's the radius, right? It's the radius. So in circular motion, that amplitude is like the radius of our circle. Okay? So how can you express the max in terms of, if we didn't know these values and you want to define the max, so how could you express it in terms of, call M the midline? In terms of the midline M and the amplitude A, how could you express the value of the max? How would you get the max from the midline and the amplitude? Adam?
Is your max your midline plus?
He wants the midline plus the amplitude. Yeah, because you're going to, so from 0, if you go up to the midline, and then you're going to add on the amplitude to get the max. So it's M plus A. And how would we get the min? Yeah, go to the mid. Always go to the midline first, and then from the midline, now we're going to go down A. So M plus A, M minus A gets you the max and min. So the max and min are like last if you're trying to determine them. Get that, find that midline, determine the amplitude, and then the max and min just are A above the midline, A below the midline. So those are just some terms, amplitude and midline. Any questions on that? So we're working towards putting all the pieces together so we can model these cyclic real-world situations with different cosine and sine curves. So we're going to make transformations to the sine and cosine so that it can model real-world things. There's all kinds of things in nature and in science that have this type of cyclic nature, right? That comes from, that we can model with circular motion. So now by transforming sine and cosine graphs, we can model real-world applications. Okay, so in order to, we've still got another piece of the couple pieces of the puzzle here. So here is a bike pedal. And so just so that we're got our terminology down, we're going to be focusing on the pedal on the bike. So this is a page in your book. I think it's 275. Nope, 279. 279, number 4. Okay, so it says, so just that's where we're going to be. It says one rotation, a bike on the rack at the bike shop. The technician can turn the pedal with his hands, causing the back's bike wheel to rotate as he turns the pedal. For every 1 radian, the technician rotates the pedal counterclockwise. The wheel spins 4 radians counterclockwise. Okay, so you can imagine this here. So as the pedal is turned, for every 1 radian that the pedal is turned, the tire valve rotates 4 radians. And if you want to, you can see those angles there. So here, I'll show you one. There's about 1 radian of angle of the pedal. Oh, is it not circle? Is that a circle, or would that be a really hard bike to ride? Yes, it would be really hard bike to ride, right? Awful, not working, not functional. Let's see if we can get one here. How about now? Better? Okay, so now we have a working wheel. Good. Okay. So again, for one radian of pedal angle results in the tire valve or the tire turning 4 radians. Okay? So what angle will we need for the tire valve to make one full rotation? So what angle should I turn the pedal so that the tire valve makes one full rotation? Think about that. What do you think about that? How many radians should I rotate the pedal so that the tire valve makes it all the way around once? What's that? 1.5. 1.5 radians. Is that right? 1.5 radians. Yeah, so 1.5 is close, but that's not exact, right? How do we get the exact angle? So what angle in radians do I rotate the pedal to get a full rotation of the tire valve? What's that? Yeah, so he's taking a full rotation dividing by 4 so that this will make a full rotation of 2 pi. So what is that, 2 pi over 4? Pi over 2, right? Okay, so we want to write, we're working this, so look at question C. So we want to write a function, we'll do it in blue here. And what does that function say? That outputs the horizontal distance of the pedal from its vertical diameter in radius lengths as the pedal rotates theta radians. Okay? So what? We're going to call that function f. It outputs the, again, this is number C at the bottom of 279, the horizontal distance of the pedal from the vertical diameter in radius lengths as the pedal rotates theta radians. What function is that? What's my input quantity? And what rule on theta will give us horizontal distance? Do I need something in front of the cosine? Do I put the radius in front? Yes or no? We want the output to be in what? Radius lengths. That's what cosine gives us. Doesn't matter what the size of your circle is. It'll always give you a fraction of the radius or number of radius lengths that you are horizontally, right? Horizontally. So just leave it just like that. Sorry about the blinking. I don't know what that is. Okay. So now, turn the page. We want an expression of theta to define the angle rotation of the tire valve in terms of the angle rotation of the pedal angle. So we're looking for the angle swept by the tire valve. In terms of the angle swept by the pedal. So given the angle swept by the pedal theta, what would the angle swept by the tire valve be? Angelica suggested 4 theta. What do you think? So what was the original thing? For every 1 radian of the pedal, we get 4 radians of the tire valve. So for every theta radians of the pedal, we would get 4 theta, right? Okay, so now we want a function g, part E, that outputs the horizontal distance of the tire valve horizontal from the wheel's diameter in radius lengths if the input quantity is theta. See if you can write that function. So we want g to output now the horizontal distance of the tire valve for an input of theta. See if you can write that function. All right, what do we think? Carter, did you get this one? What is the G? First of all, what's the input into G, according to the way they defined it?
Theta.
Still theta. But now the output is the horizontal distance of the tire valve. Did you get this?
So it's sine.
Sine. Sine of what?
The it's just sine of theta. Right?
Sine of theta. Agree with that. G.
Oh, sorry, cosine of theta.
Cosine of theta. So it's the same as this. All right.
Multiply them by 4. So
So if we want the output to be horizontal distance for the tire valve, then our angle needs to be what angle? The tire valve angle, right? So if we want the output to be the horizontal distance of the tire valve, then that input has to be the tire valve angle. It can't be the pedal angle. So now our argument represents the angle corresponding to the output that we want, right? So the argument is the angle that corresponds to the output we want. We want an output relative to the tire valve, so our argument must be the angle of the tire valve. Make sense? Argument is the tire valve angle, therefore cosine will give us a horizontal distance of the tire valve. Okay, what is the period? What is the period of F? Someone said 2 pi. Agree with that? Yeah, just our plain cosine function, our period is 2 pi. All right, what is the period of G? So what we're saying is, we're saying what's going to make that, what angle theta will make the tire valve do a full rotation? What angle of theta will make that tire valve do a full rotation? Will it be 2 pi? Okay, yeah, so it'll be, so what we have to do is, we have to look at the argument. So we know cosine's period is 2 pi. So we need that argument to reach what? 2 pi. And then whatever theta makes that argument reach 2 pi, that's saying that the tire valve makes a full rotation. So we'll call that theta p for period. And what is the period? Pi over 2 pi over 4 or pi over 2. And that's what we said before. We said, we're saying, what angle of theta makes that thing go through one cycle? Pi over 2. Sorry. It's touchy. Okay, so it's that angle of pi over 2 that gives us one full cycle. Well, that's the period then. That's the period of G, pi over 2. So let's talk about the graph then. So look, we're multiplying by 4. Did that make the period increase or decrease? Here our period was 2 pi, and then we multiplied that angle by 4. What happened to the period? It decreases, right? Because the period is the amount of input to get one full cycle of output. So if that angle is spinning 4 times as fast as the pedal, it's going to take less angle to make a full rotation, not more, right? It's going to take a quarter of the original period to make a full rotation of a tire valve. Okay, so let's talk about the graphs. So first of all, graph F. Can you graph F? So you can do this on that, right? So we're graphing F on item G on page 280. Sketch F. And spread out the, on your x-axis there, make 2 pi fill up that whole x-axis, okay? So make 2 pi fill up that whole x-axis, so spread that over 1, and then sketch function f, which is the pedal graph function. Okay, it should be really easy. We should have this down by now. Where does it start? So where will the pedal graph start? At the min, the midline, or the max? Starts at the max. In the first quarter, it goes to midline. And then second quarter, down to the min. -1, right? And then back to the midline. Horizontal distance is 0. Then horizontal distance right is back to 1. Okay, so now we got to think about what's our period of the G function. Pi over 2, because for pi over 2, the pedal angle, we know that the tire valve rotates 4 times as much or makes a full rotation in pi over 2. So I'm going to graph that pedal graph over to the right again. So when I start drawing the G function, what will it look like? So see if you can sketch that right on top of the function of f that you sketched there in the middle of the page. What is, when I'm going to start rotating the pedal, and the tire valve graph for G is going to start being swept out, or being plotted. What will that look like? Okay, compare it with the person next to you. See if you agree. Compare with what you're doing here. So what I did, that's the f function. So that's the f function that you've already drawn. So what will G look like when I start sweeping out the pedal angle, theta? So what will it look like? What's that? He said same but a lot skinnier. He did this with his hands. Why? So if we're multiplying the angle by 4, why does it make the graph a lot skinnier or crunched together? Can anyone explain it? Nathan? Right. And how long is it? One period. Pi over 2. So as soon as the pedal hits pi over 2, that tire's made a full rotation. That's one cycle. And that's the period, pi over 2. Okay? So every quarter turn of the pedal gives us a full rotation. So in one period of F, our pedal function, we get 4 cycles of the G function. So multiplying by 4, does it make the period longer or shorter? Shorter. And hopefully this illustration is helping you see why. Okay? Multiply that angle by 4. It makes that angle sweep out that many times faster, so it's going to complete a cycle quicker. Right? Yeah, Angelica. What's that? Can a period be greater than 2 pi? I'm so glad you asked. Look at, so go to number 5, and let's change that h function. Change it to sine, okay? So it says h of theta. So just at the top of the page, don't read anything, and just write h of theta equals 12.5 sine theta over 2, okay? So write h at the top of the page. Don't read anything. And let's see if we can figure out what that's talking about, okay? So I'm going to reset everything here. So we've got h of theta equals 12.5 sine of, I'm going to change, theta over the 2 is the same as 1/2 theta, right? Is that the same? You okay? So what is the 1/2 theta? What quantity is 1/2 theta? What quantity is 1/2 theta? Probably. All right. So we're kind of using our intuition here, or using some deduction. So 1/2 theta. What quantity does it represent in the context? Is it an angle? Is it a distance? What is it? First of all, it's an angle. Okay. So we're assuming it's an angle swept counterclockwise from 3 o'clock. What angle is it? Of what? You got two possibilities. Yeah.
Of 2 pi.
No, I'm asking about in the context. What angle is that talking about? The angle of what? Swept counterclockwise from 3 o'clock. Yeah, there's 2 circles, right? Which circle? So it's either the pedal or the tire valve. Is there any evidence for one or the other there? Is there any evidence, looking at the h function, that might be about the tire valve or the pedal?
Would it be of the tire valve because of the 1/2 theta? And so, just on the front, so last.
I got it.
Yeah.
It's alpha because just one radian, like how you have H input, that'd be the input and that'd be the output. So it's a big tire.
You think it's a big tire. The angle swept counterclockwise from 3 o'clock of tire or pedal? Okay, there's a couple clues that it's of the tire valve or the tire. First clue is we're calling the pedal angle theta. Okay, that's kind of the first clue, and that our tire valve is some angle, so multiply that. But then there's another clue in the h function. What's the other clue? This is talking about the tire. Yeah, so this 12.5. Did we read that in the? Yeah, so that we kind of skipped over it. In the previous question, it says the tire valve is 12.5 inches from the center of the circle. Okay, so this distance right here to the tire valve is 12.5 inches. So the fact that there's a 12.5 gives us a high degree of confidence that this is talking about the tire valve. Okay, and that's what it is. All right, so 1/2 theta is the angle swept counterclockwise from 3 o'clock of the tire valve. So how is the tire rotating relative to the tire valve? If I were to rotate this pedal, how are you going to see the tire valve rotating relative to that? What's that? Angle swept by the tire valve will be what compared to angle swept by the... Half as much. So is it slower or faster? Slower. You see it's... Oh, I never switched it. Sorry. Okay, so sweeping angles in the tire valve, or the pedal, you see that tire valve is going slower. All right, so what angle of 1/2 theta will give us a full cycle? What angle of 1/2 theta will give us a full cycle or a full rotation of the tire? Listen closely to my question. What angle corresponding to 1/2 theta, or what interval of angle of 1/2 theta will give us a full cycle? No, 1/2 theta. What is 1/2 theta? That's the argument. What does the argument, what interval of angle does the argument need to go through so that sine gives us one full cycle? 2 pi. When that argument reaches 2 pi, our h will give us a full cycle of output values. That's what can give us the period of h in terms of the input theta. 2 pi over 1/2 is 4 pi. So, Angelica asks, can the period be greater than 4 pi? Or sorry, greater than 2 pi? Can it be greater than 2 pi? How much angle does it take on theta, the pedal, to get one full rotation of the tire valve? 4 pi. I gotta turn that pedal 2 full rotations to get that tire valve to make 1 full rotation. So its period is twice as great. Its period is 4 pi. Okay, so let's. So I want you to see if you can sketch. Let's see. The pedal graph. I want right here. So here's sine. So that's sine of theta. That's sine of theta, and that's like our pedal graph making 2 full rotations. So what's h of theta going to look like? So do you have a place to sketch this? No, you don't. Okay. So if you just, we're not going to be doing example 6. If you want to use that graph down there at the bottom of 281, this is sine. So this is relating to the pedal angle. Okay, it's sine theta. And the question is, what will 12.5 sine of 1/2 theta look like? What will 12.5 times sine of 1/2 look like? Now that we know what this period is, right? The period is how much? 4 pi. It takes 2 rotations of the pedal, 2 full times around, to get that tire valve once around. So what will the graph look like? The graph of h. What will the graph of h look like? Can you describe it? Can you sketch it? Daniel, what do you think this graph is going to look like for h?
More spread out.
More spread out. So how much? Can you describe?
The minimum's going to be at 2 pi. Instead of like the last one, I was.
We got sine now, right? So is the minimum at 2 pi? So we're doing vertical height now. Vertical height above the horizontal diameter. You're thinking cosine. You got the right idea. You're thinking cosine, but this is sine now. So what will happen at 2 pi? So sine, where does sine start? Sine starts at the midline. So when the pedal has gone 2 pi, what will h have done? Yeah, Naz. Okay, so that's another issue. We're really focusing on the angle right now, but that's true. Yep, it's going to be 12.5 times this way, right? We're focusing on the angle. So, yeah.
One complete cycle from 0 to 4 pi.
Okay. So there's half of the pedal angle, or the pedal angle makes a full rotation. The tire valve makes it only halfway. Pedal makes another full rotation, tire valve makes it. So, if you multiply by a number less than 1, if you take a fraction of theta, what does that do to the period? Make it less or greater? Makes it greater, right? Because the angle is going half as much, half as fast around. So you need more angle to get it all the way around, right? Does this make sense? Okay, any questions on that? Okay, so now what we're talking about, so far we've talked about these arguments, these expressions that go into sine and cosine. Before today, they've always been functions of time. But it's possible that the argument can be a function of just another angle. Okay, the argument can be an expression of an angle. Okay, and so this is an application of that. You've got the one angle, the input angle is your theta, and then your argument is some other thing turning, right? Some other angle, in this case the tire valve, based on the angle of theta. So the argument doesn't have to be an expression of time. It can also be an expression of just plain old theta. Okay, now let's look at something different again here. Flip to page 285. And I want you to start working on look at number 2 on page 285. Read that carefully so you get familiar with the situation. Okay? Read page 285, number 2. Okay, so when the pedal is at 0, the tire valve starts at negative pi over 4. What's that? No, it's radiant clockwise, right? Pi over 4 clockwise. That's an angle of negative pi over 4, right? Yeah. So that the tire valve starts at negative pi over 4 when the pedal is at 0. Okay? So in that table there it says at pi over 6. How would you calculate now the new tire valve angle? And write it in an exact value. How would you write an exact value of that tire valve angle now if the pedal is at pi over 6? What do you think? No calculator, just an expression. What would it be? Yeah. Pi over 4 minus pi over 6. No, there's no times in it. So we've got the pedal angle's pi/4, and how far behind is the pedal angle? Sorry, the pedal angle is pi/6. How far behind is the tire valve?
We just do pi/6 minus 5.
Pi/6 minus pi/4. And what about at, here is 2.44 radians for theta. 2.44 radians. How would you describe what the tire valve angle is?
Would you do the same thing, just subtract
Yeah, tell me.
negative pi/6?
What?
You just subtract negative pi.
So what's the expression that gives this angle right here? Tell me the whole thing. If this angle is 2.44, how would you get the angle that the tire valve is from the 3 o'clock?
2.44 minus negative pi over 4.
Not negative, just minus pi/4, right?
Yeah.
Yeah, 2.44 minus pi/4. So the valve angle equals what? As an expression of theta. What is it? Yeah, theta minus pi/4. Okay, so are we doing, they talking about sine or cosine here? Vertical distance above horizontal diameter. Okay, so if I want the vertical distance above the horizontal diameter of the pedal, what is that? Sine. P, we're calling that P. Okay, so the vertical distance above the horizontal diameter of the pedal is sine theta. And then they want T. T is the output's vertical distance above the horizontal diameter of the tire valve in terms of the pedal angle theta. So can you write an expression? Oh, this should be right now. Can you write an expression for T of theta? That's E. Question E on 286. Go. Can you do that? T of theta is going to output the vertical distance above the horizontal diameter of the pedal.
In terms of radians?
In terms, yes, outputted in radian measure. Candace, have an idea about that? So we want the vertical distance of the tire valve. So would that be sine or cosine? That's sine. And so now what's our input angle? If it's about the tire valve, then we need the tire valve angle there, which is what? How are we expressing that tire valve angle in terms of the pedal angle? Yeah.
If you like sine theta minus pi/4.
You want sine of theta minus pi/4. That's it. So if the output is about the tire valve, then what goes into sine has to be about the tire valve. And that's our theta minus pi/4. Okay, so what's this going to mean for the graph? So we know what sine theta looks like. Let's graph that. So here we go. There's 2 cycles of sine. Just sine as itself. That's the pedal angle. So then the question is, and we'll put that over there. So that's that same one. That's the same graph, okay? What is the tire valve, the T function, how is that going to graph? How is the T function going to graph? So Is the valve angle, is it ahead or behind the pedal angle? Is it ahead or behind? It's behind. It's lagging behind. How much is it lagging behind? Pi by 4. So in terms of increasing theta, it comes after, right? So if theta increases this way, what does it mean for that cycle to come after the blue one? It's lagging behind, so it's going to come after. So is it going to start further to the right and end further to the right, or is it going to start further to the left and end further to the left? It's behind. So think of the angle increasing this way. So first comes sine, right? First the P graph starts. And then later the T graph starts. Do you see? So is it going to be shifted to the right or shifted to the left? So the question is, can you see why? So watch. So here we've already started the pedal graph, the blue, that's the P function. And then now starts, and where are we? What angle are we at right now? We're at pi over 4. Oh, darn it. There we go. So now starting at pi over 4, that's when the tire valve cycle starts, you see? So you need to see that red graph as being to the right because the cycle is starting later. It's behind. You see that the red graph is behind the blue one. Because the tire valve is lagging behind, you need to go forward more angle before its cycle starts. Does that make sense? So what we're trying to motivate is, why does subtracting, do you see why subtracting this right here moves the graph to the right? Because the tire valve, it starts its cycle later. It's lagging. It starts, and later on the theta axis means to the right. This comes after this in terms of increasing theta. It's a huge point. Can you see it? A greater angle of theta is later. It's after, lagging behind.